actually boson had sort of various modes. There were some center of mass modes, and then there were these oscillators. Okay. And we define some kets, which are again functions of p, of the momentum. And then you can start building other states from them by acting with the creation operators. So you start with p, then you have a1p, a1 square p, and a2p, sorry, minus 2p, a minus 1 cubed p, a minus 1, a minus 2 p, a minus 3 p, etc. So if you remember, right, each of these modes contribute. So what is the energy of these modes? Which is, well, sorry. Here I was sort of ignoring the fact that there are actually two sets of modes, the holomorphic and anti-holomorphic modes. So this is kind of a half of the actual state. So a state in this theory can be written as a sort of tensor product of a left of an holomorphic and anti-holomorphic states. So each of these has the same momentum and is built out of A's and A bar. So an actual state of the theory might look like this. A minus 1 squared, A minus 2 bar P. Okay? But the holomorphic and anti-holomorphic modes commute with each other. So typically we will just focus, say, on the holomorphic modes and then put them together with the anti-holomorphic modes to get a final answer. So if you act with L0 minus 1 over 24 over P, you get P squared over 2. The same if you act with L0 bar minus 1 over 24. So the total energy is the sum of these two operators. So the energy of a state is a naught plus a naught bar minus 1 over 12. The momentum, the worksheet, the momentum on the worksheet of the state is a naught minus a naught bar. Let's not confuse the momentum as momentum along your two-dimensional space. And P, which is the conjugate momentum to the center of mass, degree of freedom. So this is associated to translations in space. This is associated to translations of the scalar, shifts of the scalar field by some constant. Okay. So every time you act with one of these modes, you raise the energy by 1, by 2, by 3. So if you look at L0 minus 1 over 24 for these states, you get P squared over 2, P squared over 2 plus 1, P squared over 2 plus 2, p squared over 2 plus 3. Usually this integer is called the level of the state. So at level 0 you have one state, level 1 you have one state, at level 2 you have 2, level 3 you have 3. In general you get the partitions, the number of partitions. How many ways you can decompose the total level into 1s, 2s, 3s. So the number of states actually goes pretty fast. Okay. Now, last time we also mentioned the Fourier modes of the angular of the stress tensor, which, as I mentioned, generate Virasoro algebra. So these guys satisfy computational relations. They look like this. Correct me if I'm wrong. Was there a minus sign? I left my notes. It's probably a minus sign. A plus sign? Yeah, it's a minus because a minus m is supposed to raise the eigenvalue. Yeah, those notes were just for my personal consumption, so do not necessarily trust all the formulas there unless you check them yourself. Okay, something like that, right? So now if I start with my state P, so this satisfies, this is killed by all the lowering, by all the modes which lower the energy again. This simply follows from the fact that this guy is actually built out of A's with positive. I mean, it's normal order, so that there's always an A with positive index which kills P. Now you can ask what happens if I start building states using the L's instead of the A's. So the expression for L was, again, check me on the signs, but something like this. I hope I got the signs right. I think so. So what happens if I act with L1, N minus 1, say, on P? So the only interesting term is going to be A0, A minus 1. So I get minus P, A minus 1. Okay. Now let's check if this makes sense. Well, for example, I could act with L1 on that. So if I do it, I can do it in two ways. I can use the Virasoro algebra. or I can use this commutation relation between else and A's. Sorry. Yes. Right? Or I could really expand this L1 into its definition. So I get something like A0, A1, acting on this, and then let me see. I hope I'm not mistake. I'm getting a wrong sign. I know, sorry. Sorry, I was supposed to put the minus here. Yes, and I also probably. Okay, here I probably messed up a sign. I don't know why. But here I'm supposed to get, again, p squared. Anyway, so, okay, we can keep going. For example, you can say, okay, what happens if I do a minus 1 squared of p? Okay. Now you have to or I can do a minus 2 of p. And get something like that. So you see, if I build my states with L's instead of A's, I just get different linear combinations for the same states I got there, of course. But what I want to point out is that for generic P, these linear combinations are just distinct. So for general P, you can build your tower states by acting with A's, or you can build your tower states by acting with L's, and you get the same result.
If I build my states with A, then I have this degeneracy per level, right?
Yes.
But if I act with the L's, that degeneracy is not upper and third, right?
These are true. Yeah.
Because, I mean, if I act with, for each state that I act with L minus 1, I have a linear combination of the states
Yes.
that are at the same energy level. But there are still other linear independent states that I can construct with L minus 1.
Right, so there is the same number of building blocks, if you want. There are L's with indexes -1, -2, -3, and so on, or there are A's with indexes -1, -2, -3, -4. So unless some miracles happen, you expect these two things to coincide. But for special value of the momenta, perhaps these two can actually not coincide. So what can happen is that acting with L's, I actually don't populate the whole tower. So when that happens, usually, the way to say that is that there is a null state. So there is something built out of L's acting on P, which is actually a 0 state. Is not there. So the first example you find from the identity. So suppose, for example, that P is 0. Then clearly you don't have this state, or neither does. So if P equal to 0, you lose L minus 1P and everything else that is built out of it. So if you have this sort of big triangular tower of states, you're losing a whole sub tower, which starts with minus 1P. Now, you can ask, when do you lose a state at level 2 instead? And here, I strongly suspect I must have made a sign mistake, because for real P, I'm not supposed to lose any states at level 2. While from this, it looks like if P was 1/2. Sorry. Yeah, if P squared was 1/2, I would be. I think that I must have gotten, well, probably not a sign here, because these are just applying the definition. Here. That formula was right? That one up there, the commutation between AN and AM was right? And these are not, so should be right. Sorry, I just forgot to bring in my note. So there is a sign mistake here. Okay, so supposed to be, these are supposed to be linearly independent for all real value of the momenta. Perhaps I just forgot an I somewhere. Maybe A0 was supposed to be IP. I forget. Anyway, I'm sorry. We'll get it right. But right. So anyway, you see that for special value of the momenta, you might have some coincidences, some state. You might find some states built out of A's, which are not built out of L's. Okay.
The A modes are basically bosonic modes, the usual ones that one has met of the prescalar field, but the L's are, they appear to be also like some sort of ladder operator that create other modes. Which are those modes? What's the fundamental difference between creating states with L than creating states with A's?
Well, you can imagine both A's and L's as generating some symmetry of your theory, because they're conserved charges for some currents, some conserved currents. So these are just two different types of symmetry. And we are acting with these symmetries on the ground state. Okay? So the symmetry generated by A's is just shifting the scalar field by some function of the positions. So it sort of is adding some excitation to the scalar field. On the other hand, the L's, if you remember how they act on the scalar field, they act as ephemerphisms. They take your scalar field and they reparameterize the coordinate inside. If the change of coordinate blows up towards the past, you actually excite the field by doing, excite the ground state by doing a coordinate transformation like that. So it starts with a scalar field which, But I think this should become clear in a later lecture, in which we study conformal transformations, holomorphic coordinate parametrizations. Now, okay. So for one single free scalar of standard signature, the story is pretty straightforward. For generic P, generic real P, you get the same tower acting with the L's or acting with the A's. For P equal to 0, you get something special at like 1, and that's it. So now the states of a theory which cannot be obtained by acting with L's on something else are called primaries. So in general, whenever you have Virasoro algebra, you call primaries or highest weight vectors which are annihilated by all the positive L's. Sorry. The primaries are the ones that are annihilated by all the L's. The ones that are generated by acting with negative L's are called descendants. So in a theory of a free scalar, the primaries are the P's and also A minus 1, 0. And that's it. And everything else is a descendant. Now, if you start having multiple scalar fields, clearly you start having many more A modes than L modes. Well, let me be more precise. Of course, if you have two scalar fields, you're free to think in terms of the stress tensor of each scalar field separately. And then again, you just get two copies of this story, one for each scalar field. But it's also useful to think, when you have several scalar fields, you also want to think about the total stress tensor. So if I have a bunch of scalar fields, for now, still standard, okay. Then, so this is a bunch of copies of a scalar field, independent copies of the scalar field. So I can define a total stress tensor and its modes. Just by summing up all the stress tensors of each individual scalar field. Notice that this is invariant under rotations of the scalar field. So the stress tensor is, of course, invariant under the SOD that rotates these scalar fields. So if I just think in terms of this total stress tensor modes, clearly I have much fewer of these modes than I have of A's. So I will start finding many more primaries. For example, if I act on some state with momentum by L minus 1, I get something like AI. Okay. So I only get, I don't get all the AIPs, but only the one aligned along the momentum. So you can guess that the ones that are aligned orthogonal to momentum are going to be primaries. So let's check. I can take a state. Let me write this. So let's check if a state like this can be killed by L1. It's surely killed by L2, L3, and so on, because they would try to make it have negative energy. But when you compute L1 over this state, you get something like so it means that if your polarization is orthogonal to the momentum, is the primary. And so on. You can start checking for all the states that you can build out of A's, which ones are primaries. So you can decompose your space into what are called Fermat modules, which are the tower of states generated by the action of the L's over a primary. So we find now a bunch of primaries. P, you find so I minus 1p with epsilon I pi equal to 0. We can perhaps do the next level too. So you can look for something like this. So you can ask, when is this guy going to be a primary? So you add to L1, you get something like EI minus 1j epsilon ij plus epsilon tilde I minus 1, roughly. You want this to be 0. Then you act also with L2. You want that to be 0. You get something like epsilon II plus pi epsilon tilde I p equal to 0. So you get a bunch of constraints on the coefficient of these states. I don't know, this tells you that epsilon tilde can be identified with the part of epsilon ij along p. And this tells you that the trace of epsilon is related to epsilon contracted with p. Okay, so you get relations like that. So this defines a bunch of primary fields. And then you get your descendants. Now, for now, the Hilbert space we've defined for standard scalar fields has a nice positive definite inner product. So you can define a bunch of brass and kets. And then if you start, so your states are killed by the negative modes. Your brass are killed by negative modes. Okay. You can define descendants in this dual space by acting with positive modes. So you have P, you have A1P, H2P, A1 squared P. And that will define inner product between any brass and any case. For example, suppose I want to compute the inner product between P and A minus 1P. Okay, this is 0 simply because A minus 1 kills the brass. If I put an A1 here, then I can have a chance of getting something on 0. use the commutation relations, and I should always put a p prime and get a delta function. But just for convenience, let me just pretend that this is 1 when p is not p prime. So I'm just going to write, no, okay, I don't need to do it. So you can commute the 2. This drops out. So you can compute the norm or the inner product between any of these states. Pretty much the only thing that gives you non-zero is if you have exactly the same number of and type of A's on one side and on the other. And the inner product is always positive. So for standard scalar field, you get a nice positive definite inner product on your Hilbert space. And this remains true also if you have several scalar fields with a standard commutation relation. Now, of course, you can also build your bras by acting with your L's. But funnily enough, if you, from the point of view of the Virasoro algebra, it's not immediately evident that your inner product is going to be positive definite. For example, well, if you compute something like this, you get something like p squared. Well, that's okay. So we knew that this state was going to be funny if p is equal to 0. But in generally, you know, if you compute with a bunch of L's, and you want to compute the answer just using the commutation relation of the Virasoro algebra, here you're going to get some complicated polynomial of p of p. And it's not immediately obvious that these polynomials are going to give you a positive definite inner product. We know it has to be the case because it was true for the A's. But if you're in a situation where that changes, then something more interesting might happen here. And now this is exactly what's going to happen for the case of string theory. Because as you remember, after we gauge fix the path integral in the bosonic string case, we had a bunch of scalar fields, one for each coordinate of space-time. And we want our setup to be Lorentz invariant, which means that the sort of commutation relations we can write involves the Lorentz matrix, which means the time coordinate is going to give us trouble. If I compute, say, the inner product for a state like this, I'm going to get -1. So our space of states is actually does not have a positive definite inner product. There are some ghosts, there are some troubles. There are some states with negative norm. Now, you might have seen this already in just in gauge theory. In gauge theory, the time-like component of the gauge boson creates states with negative norm. Gauge symmetry cures that. the constraints from gauge symmetry essentially kill the states in negative norm. Now, something similar is happening for string theory. So we still had to impose the equations of motion for the metric after we gauge fixed the metric. So classically, we require the stress tensor to be 0. Now, quantum mechanically, we can try to do it a little bit by hand, like you do in Gupta-Blewer quantization in gauge theory. So you cannot require the stress tensor modes to be 0. For example, they're supposed to satisfy the Virasoro algebra, where definitely the right-hand side is not 0. What you can do is to require all the modes that lower the energy to kill your physical states. In dually. If you do that, then the wave of the stress tensor, at least, between physical states is going to be 0. Because the modes of the stress tensor are going to kill either the physical states on the right or the ones on the left of your expectation value. Now, I said it about the LNs. I didn't write anything about L0. So you would expect I should put something like L0. So the 0 mode of the stress tensor was L0 minus 1/24 for a single scalar. You expect me to put something like d/24 here if I have many scalar fields. Now, to get the right number there, one has to do things more carefully. You need to really do the full BRST quantization, and we're going to do that in the next lecture. For now, let me just tell you that the correct answer is 1. In a sense, so there's an extra contribution to the Casimir energy, which comes from the path integral over the matrix on the worksheet, and that corrects the Casimir energy exactly to -1. Also, something which you cannot immediately see from here is that the total dimension, the number of scalar fields, is going to be 26. What we also see today, perhaps, is that 26 is an interesting number, at least. Okay, so these are the correlations of physical states. Now, as when we do electrodynamics, besides constraining the physical states, we also have to get rid of some null states. Some states of, so this condition by itself, although it's not evident, is sufficient to prevent states of negative norm. But it still allows a bunch of states with 0 norm that you want to get rid of. These states are states that are orthogonal actually to all the physical states. See, if I take any state which can be written as L minus N acting on something, and I contract it to the physical state, I'm going to get 0. So the claim is that the spectrum of bosonic string can be reconstructed by taking your scalar fields, imposing that there are primaries of L0 eigenvalue 1, and they're not descendants of some other primary. So now I've wrote it everything for L. Of course, there is also a bunch of conditions involving the L bars. So now we can analyze this problem level by level. Start from our ground states, see if there are any physical states there in descendants, then move to the first level states, check if there are any physical states, any null states, and so on. So let's start from the ground states. Well, the ground states, we already know, are primaries. And they're definitely not descendants. I cannot get this guy by acting with L minus something on something else. So the only condition we need to impose is that L0 minus 1, that these states are here by L0 minus 1 and by L0 bar minus 1. These conditions are equivalent because these states have an eigenvector, eigenvalue p squared minus 2. So the condition is that p squared equal to 2. So the physical states that come from the, so what does it mean? This means that I'm taking my string, okay, this is propagating in space-time. I'm not exciting any vibrations to this string, just moving as a blob, featureless blob, with the center of mass moving at with some momentum p. This tells you that this state is physical if p squared equal to 2. I'm working with the convention where the space components give a positive contribution and the time components give negative contribution. These are actually tachyons. So the bosonic string, the first state you get from bosonic string is a tachyon. Definitely is not very promising. Indeed, the bosonic string theory is sick. One of the states, the first state that you encounter is a tachyon. So there is some sort of instability in bosonic string, and nobody really knows where that instability actually goes to. So presumably bosonic string decays to something. We don't know what. Okay, let's keep going. Now we can look at states of level 1. Okay. So we found the condition for the states to be primary. So the condition is that the sort of polarization has to be transverse to P. We want them to have eigenvalue 1. That means that P squared is 0. But then, if P squared is 0, something funny happens, which is that if you look at the null states, n minus 1. But what happens, right? So this is p mu, and mu minus 1 p. And this actually satisfies this condition. So one of the physical states is actually a null state. Now, and this happens exactly because that number over there is, so because this number is minus 1. Okay, this had been minus 26 over 24, minus 1 over 24, whatever. Then you would get a p squared different from 0 for these states. And then these null states would not have been also a physical state. So for generic values of this constant, you would get a bunch, okay. You would get a physical state for every choice of epsilon perpendicular to your P. But because there is a minus 1 here, you actually lose one of those as a null state. Now, If I could for a moment close my eyes and ignore the fact that there are L bars and A bars and so on, this should remind you a lot of electromagnetism. See, this is a single particle state, okay, that comes from exciting this string. It carries a spinor index. Sorry, it carries a vector index. So it's like a gauge boson. If I try to build a field for this particle, I would use a field which carries an index, some sort of A mu. And this would tell me that this would be sort of the polarization of this gauge boson. This would tell me that polarization has to be transverse, that the gauge boson has to be massless, and that I should throw away gauge states from the point of view of electromagnetism. This is just a polarization which is actually longitudinal. So in this, if I was able to ignore the A bars, which I'm not, okay, then out of this I would get something like a gauge boson, which is nice. Now, actually, I do have A bars, so the actual state at level 1 I'm talking about has to look more like epsilon mu nu, A minus 1 mu, A bar minus 1 mu, P. So I was ignoring it for a moment, but actually, see, I need to impose both set of conditions. And I cannot have a state which is like that, because that would have a different eigenvalue for L0 and L0 bar. So in order to satisfy both L0 minus 1 equal to 0 and 0 minus bar minus 1 equal to 0, I really need to look at the state like this. And then the statements I was writing there remain very similar. So P square is 0, and epsilon mu nu is orthogonal to both P mu and P nu. And I want to throw away null states where epsilon mu nu is P mu u. So the string states I get at level 1 are actually objects which carry two indices, two spacetime indices. So let's try to see which sort of field is this, which sort of particle is this. Something of spin tube, massless, transverse, and it has a gauge symmetry. If I was trying to build a field for this, I would use some sort of field that looks like this, and has a gauge symmetry. Well, actually, it's convenient for a moment to decompose this into a symmetric, antisymmetric, and traceless parts. So there will be a bunch of states where I symmetrize and take away the trace. A bunch of states where I antisymmetrize and then some where I take the trace. And if you look at the gauge transformations of this, so essentially this is a spin tube particle, massless, with a gauge symmetry. This is the graviton. There's actually a theorem in field theory that whenever you have a massless spin tube particle, and you try to write down Feynman diagrams which make sense, which are gauge invariant, all the couplings, all the all the couplings for these gravitons are fixed. You discovered a massless spin-2 particle has to couple to everything else exactly the way a graviton would. So as long as string theory behaves like a field theory at low energy, you already know in advance this is going to be a graviton. So this is nice. The tachyon was bad news, but the graviton is definitely good news. So bosonic string theory has automatically a graviton. There is also other stuff, unfortunately. So there is a graviton, but then there is this weird thing, sort of something that carries an antisymmetric index, space-time index. If you're writing a field for it, it would look like a true form. It's called the Cadramon field. And then there is an extra scalar. So bosonic string has a set of massless fields. So there is the tachyon, then there is a set of massless fields, which are a metric, a true form, and a scalar field called the dilaton. So this metric has a gauge symmetry, which is a parameterization of space-time. This is a gauge symmetry, which is something like this, sort of a true form version of the gauge symmetry, of the standard gauge symmetry of a gauge field. Okay, so we'll, in order to actually see how these fields interact and what they are, one actually needs to look at scattering amplitudes, try to see what are their interactions. I mean, we already know that these scattering amplitudes are almost surely going to give us a graviton which behaves like a graviton. But you can still ask, well, how does this other field, how do these other fields behave? What's their role? Why are they there? What do they mean? And that we'll learn as we progress. So if you now look at the other string states, the ones that are built at higher levels, built out of things like a-1 mu, a-1 mu, or a-2 mu on the left, and the same things on the right, on the entelomorphic side. Then you get all sort of other states. Now, for these states, b squared is going to be -2. So these are going to be massive states. And in general, if you put a bunch of oscillators with a total level of n, this gives you a moment, a mass which is n-1. So this tachyon, was a tachyon. Then there are these massless states, and then there are infinite towers of massive states. And with some patience, you can figure out which of these states are physical, what are the null states. And actually, we can start doing it, although I'm almost sure that I will not get the numbers right on Blackboard. But something amusing is that although you can do this calculation for every number of scalar fields, it turns out that only for 26, only when you have 26 of them, that when you have 26 of them, there are actually more null states than when you don't have 26. So 26 is special in the sense that you have a bit more null states to get rid of than you would have otherwise. I don't know how interesting one might consider this, but it's just a fact. So, right, if you look at level 2, we will start so let me for a moment pretend that we only have holomorphic modes, and then we'll put the antilomorphic modes in. we start with space like this, and we try to figure out which ones are primaries, which ones are physical.
So you created, for example, the case of the tachyon by acting just with the holomorphic creation operator, right?
I didn't do anything for the tachyon.
So is there a counterpart with the anti-holomorphic one?
No, in the tachyon, I didn't create anything. Right? I started just
with
the ground state.
So the thing is that is there any duality by using the anti-holomorphic and holomorphic operators as if it's particle and antiparticle?
No, I mean, see, at the moment, if we want to build states, we have to use exactly the same number of holomorphic and anti-holomorphic guys. So I always get my fields always carry 2 copies of some structure. Like I don't know, here they carry 2 Lorentz indices, each of which is associated to a gauge symmetry. If you make your theory a little bit more complicated, you can find situations where the left and right movers can be a bit more different. But yeah. I mean, if you want to exchange left and right movers, what you do is sort of a reflection in the worksheet of a string. That it is a symmetry of the theory. So it's going to act, sensate B to minus B, keep G and phi fixed. So this is going to be one of the symmetries of string theory. And then you can try to ask. You can try to ask if you can do something interesting with this, with symmetry. But we'll see about that. So, okay, so well, I don't really have the time to do it in detail, and it's a good exercise though. But to sketch it, right? So we more or less already saw. Well, I erased unfortunately. If you want this to be primary, you start getting relations like epsilon mu nu p mu plus epsilon tilde nu equal to 0, epsilon mu mu plus p mu epsilon mu tilde equal to 0. Okay. And then you ask, are there any null states in here? Right. So the null states are going to be states which are generated by L-2 acting on P, or N-1 acting on N-1. So you can try to look if some linear combination of this sort can take this form. And you should find it that this happens only if the total dimension is actually 26. Which, I mean, doesn't mean much in the sense, it's not this that tells you that the dimension is 26. Just something interesting. Although, right, what you can also check is the dimension was bigger than 26. You might actually get in trouble and have physical states which have negative norm. So 26 is sort of the boundary where if you go beyond that, something bad happens. And if you are at 26, something interesting happens. So you have non-null states on one for less than 26 dimensions. So everything has positive norm for less than 26 dimensions. You have some null states at 26, and then you get negative norms bigger than 26. Okay.
Could you just repeat how you get these conditions? How do you know that if this is satisfied, then the state is a primary?
Sorry, I just, well, I erased it, but this was the result of doing L1 over the state equal to 0 and L2 over the state equal to 0.
And in the other case, it was just L1.
Yes. Okay, so tomorrow, I guess, you get pi day. And then on Friday, we're going to do real state quantization.